Here we are again, just two guys.
Hello,
Two
everybody.
cool guys.
I'm Cody Rue, and I am lucky enough to be joined by Philip Zucker again. And this is the Church of Logic. And after this long hiatus, we get to talk about a field that I'm personally pretty psyched about, which is called Equational Logic. So, how would you define equational logic, Phil? I have thoughts, but I want to hear it from you first.
I mean, I don't know why I would be the one defining it, but it's, what is it? Equations are good. I'm down for equations. Like, I have a background in physics, and everything we do is equations, and I like things that are simple and intuitive, and the things they taught you in 4th grade and 5th grade are simple and intuitive, so like, or relatively speaking, adding numbers, maybe some, variables, things like that, and then there's some math topics that seem ripe for automated reasoning and things like abstract algebra, at least simple stuff like groups and lattices and such.
Great.
And sort of how do you study that, or how do you talk about that in a logical sense? And it seems like equational logic is sort of the framework that fits that.
Cool. Yeah, that's great. I was going to go a completely different direction, but this is much better.
You opened the door.
The different direction I was going to go in was the wrong one in retrospect. I was going to say, hey, I explained first order logic, in a previous episode. I'm just going to say what the axioms are for equational logic. It's just some theory, right, where the only relation you have is equality, and you have some axioms for equality, but that's not the way you explain it to a human being, and that's the way Phil went, explain it to a human being, which is just way better.
Here's the thing. In the physics world, I never did a proof by cases, like maybe once. Like that never happened. Everything was proof by equations. Everything was rewriting. Everything was doing an integral or doing, canceling terms and stuff. And I don't know, it's a crazy mismatch, like the world I live in now and the world I lived in back then.
Yeah, I do think, proof by cases is definitely, it happens in math, but usually it's kind of a sign that things have gone wrong. And computer science is just super appropriate for proof by cases because everything's very discrete, right? It's zeros and ones, it's, constructors, you have if branches, all this is very discrete, and you sort of want to keep all these discrete parts, reason about them. You just don't get that in analysis or in calculus. Everything's sort of happening at the same time. Not to say it's simple, but it's definitely less overwhelmingly present.
Well, I think, you were starting from this first order logic perspective, and before first order logic, there was propositional logic, and it's ands and ors and implies. And
right.
That's just very casey to my taste. Whereas equational logic, it's about substitution. It's about, you have a pile of equations, and then you substitute them into each other, and you can get new equations out of that, and that is kind of what equational logic is talking about.
I feel compelled to try and define equational logic at this point, though I'm not sure how, and I never know how much detail I should go in. But basically, in equational logic, you just have equality of terms, right? So terms are these kind of constructs that look like programs or just trees. They're just abstract trees, and all you can state in equational logic is, a term equals another term, or a term is not equal to another term. And then all your hypotheses have this form as well. And then the only rules you're allowed to do is, reflexivity, transitivity, symmetry, which are the basic equality, facts. And then congruence, which is say you're allowed to replace a subterm by any other subterm which you have proved is equal. And in programming this is really useful, right? I wanted to, this is the only thing I really wanted to get across, which is when we reason about programs, we do this all the time. We have a condition true or some condition. You're like, oh, this is just equal to the second condition. You can you can replace that by the other thing, and it's okay. So all the time we reason about, is this thing the same as this other thing? And I mean, obviously, when you start postulating equalities, things get a lot more complicated, right? I mean, if you have no interesting equalities, everything's sort of trivial. And the two things I wanted to bring up there were, yes, you can think about programs as these trees, as these terms, kind of the abstract syntax. And then the equalities you can think about of these two programs do the same thing. And so equational logic becomes this really useful thing in computer science, which is, how do I reason about what my programs are going to do? And you can just use this logic. It just sort of tells you, hey, I can replace this by that. Now, there are some subtleties, but I'll get into those at some other time. And another thing I wanted to mention offhand is this logic I've sort of hinted at is complete for kind of the normal semantics, where you interpret terms as, a function application is a real function, and a constant is a real constant in some set, and then equality is actually equality. If you look at all these possible interpretations, and something is true in all of them, then it's provable in this logic. Basically, the logic has enough rules. Like in the completeness theorem, the good old completeness theorem I talked about a couple of sessions ago. So that's useful to know. It sort of says you haven't forgotten any rules in your logic. It's good enough. But, it's not that useful. One thing that's a little bit more interesting is there's a sort of one rule where you sort of have symmetry, transitivity, and reflexivity in all one go, called paramodulation. Is that what that is? And that's kind of useful for proof search. You can sort of use this single rule to think about proofs. Right, so that's sort of the main points I wanted to hit. The last thing I wanted to mention was, if your hypotheses don't contain quantified equalities, like in group theory you have, for all x times the unit equals x, right? So that's a quantified equality. It holds for all x. But you could imagine a system where there's no for alls. Everything's basically ground, right? There are no variables really, or at least the variables don't really matter. They can be treated as constants. And if your hypotheses are all like this, all ground, then actually everything is decidable. And this is kind of intuitive, but Phil is actually kind of the expert here. So I wanted to explain why it kind of makes sense this would be decidable, and two, why doing this efficiently is maybe not as obvious as you might think.
Yeah, why is it obvious it's decidable?
Well, is it? Is there a way to explain why you would expect this to sort of, this is actually, I can figure out. I only have ground hypotheses. I have, a question about an equality of two ground terms. How might I go about the most naive possible way figuring that out without some infinite search?
Well, I think it's basically a method you can use is you can sort of consider like all possible substitutions of those terms into the other terms, and then that process stops, I think. I think that there's some way of doing that right. That's not very convincing.
Yeah. The argument I have in mind is, what are all the things, all the terms you could possibly care about?
Yeah.
So the ones that actually appear in your problem, there's the ones that appear in the hypotheses, and there's also all the subterms of those terms.
Right.
And I think a basic observation, or a fundamental observation, not a simple one, is that that's all the things you need to care about. Just those. And any equality, any rule that takes you out of that realm it doesn't even need to be thought about. Any reasoning you can make that takes you out of that realm could just be tossed in the garbage. And those are just finite, so you can just tack all possible equalities, all disequalities between all those terms. Eventually, you either find your conclusion or you don't. All right, this was easily longer than I thought it would take, so why don't we do a two-parter and talk more about these equalities between ground terms and other things like rewrite systems. Let's do another one of these.
Okay.